name is Michael Bretti. I'm the founder of Applied Ion Systems. Today I'll be talking about my developments of a PocketQube class Hall thruster. So a little bit in brief going forward, this development is part of a larger development of what I'm calling the Adamant series at Applied Ion Systems, which is focusing on the utilization of a unique fuel called adamantane. And for those of you who haven't heard of it, and most people actually even in the EP field haven't heard of it, adamantane is a solid hydrocarbon, a diamandoid hydrocarbon that has very similar properties to iodine, which is heavily explored, gaining rapid traction as an alternative fuel in the field. But adamantane has a few different properties that make it particularly unique for this development effort. And while there has been some studies in the field, there's only really been about 2 or 3 papers that mention it, and really for high power gridded ion thrusters. So at this point, as far as I'm aware, AIS is the first and only company in the world actually specifically developing adamantane fueled thrusters. So why adamantane? There's a few key advantages. One, it has high molecular weight, similar to that of xenon, 136.23 AMU. Has a very high molecular ionization cross-section, which means the ability to ionize it. So it's even easier to ionize than commonly used xenon or iodine, both of which have very high ionization cross-sections to begin with. The major things, however, are that it has a very low sublimation temperature in vacuum, less than 15 degrees C, which allows for solid unpressurized fuel storage. And unlike its other cousin iodine, it is very safe, non-toxic, and non-corrosive to handle. Originally, I was going to do iodine developed systems, but there's a lot of issues with toxicity and corrosiveness that would make it unviable for me at the present time. But stumbling across this particular fuel, it's opened up a lot of doors for this development. There are some key drawbacks to the fuel. Because it is a hydrocarbon, it is highly complex with the plasma ion species, making predictions and calculations extremely difficult in terms of performance. Because it is a hydrocarbon plasma, it also tends to run dirty. It doesn't corrode or create conductive spray like other types of fuels, but it can lead to some kind of dirty coatings. In the thruster itself, particularly with neutralizers and higher pressure plasmas, amorphous carbon deposits can be an issue. And there are some beam losses and ionization efficiencies due to complexity of the ion species break up, and then some tendencies for electronegative affinity. However, these inefficiencies are the benefits far outweigh the inefficiencies, particularly for this development. On the right, you can actually see some adamantane in one of the fuel tanks, my new fuel tanks that I'm developing, and it looks literally like a coarse table salt. So it makes it quite easy to implement inside of a fuel tank. So before I got into the PocketQube Hall thruster, there were a bunch of preliminary tests moving forward. So in the very beginning of the year, I worked on some low power sublimation and ionization validation just to test this fuel to see if it was viable. Over the course of a number of tests, I confirmed that I could achieve very low power sublimation, less than 3 watts, a low degree of sublimation temperature, less than 15 C, low ionization power, less than 1 watt to a couple watts for the plasma initiation. And then over the course of the test, multiple topologies were demonstrated, everything from basic low discharge to ion beam extraction, neutralizer plume extraction, and negative charge extraction. So this really led the door into the next test for the Hall thruster development. So here we can actually see a video of one of the early tests. So this is the test cell in vacuum actually operating to simulate the extraction of a neutralizer plume for some larger class Hall thrusters in the adamantane series. As you can see, a nice, bright, stable plume that would be used if it was on a thruster for neutralizer extraction. So moving forward, I went on and developed a very low power miniature hollow cathode neutralizer. I won't go into the details of this right here because there's not enough time, but I have test reports and other information widely available from this and other tests that give more information. It's a 2-watt hollow cathode, runs on -3 kV, and can be run on really any gas. The only materials here are stainless steel and Somos Perform, which is a ceramic embedded SLA, which has actually enabled a lot of the current developments in my Hall thruster work. And the mechanism is very unique. It utilizes a cold hollow plasma cathode glow discharge instead of traditional inserts like lanthanum hexaboride or even RF power, just straight high voltage DC. So here we can actually see a video of the hollow cathode operating. This is on one of the prior Hall thrusters. So the Hall thruster isn't on, I'm just in self-operating mode with the hollow cathode. So a nice stable plasma coming out for electron extraction, which would connect to the anode when the Hall thruster is running. So here is kind of the first jump into the Hall thrusters. This is larger than a PQ size, but still kind of a stepping stone to scaling smaller. And this was really my first effort into it. So this was the AIS-EHT1 Micro End-Hall Thruster. So as the name suggests, it is an end-hall ion source, as opposed to the more common stationary layer sources typically seen on larger systems. So it's about 0.3 U in size at 182 grams. The fuel is adamantane and has a 3-gram fuel capacity. So you see here the fuel tank, there's a heater on the bottom, the electronics, the hollow cathode, and the Hall thruster are all integrated into one 0.3 U package. Total system power is about 25 watts for the system. And the expected thrust is about 30 to 100 micronewtons. ISP at this point, I haven't actually figured out yet just because of the complexity of the fuel. And that's really something that would have to be directly measured just due to how difficult it is to predict for these types of systems. So over a number of tests, I was able to achieve full ignition with the hollow cathode, with adamantane fuel in vacuum, and with the Hall thruster running at a nominal of 26 watts power. So here we can actually see the Hall thruster operating stably in high vacuum. Those flashes are actually from the Faraday cup breaking down. The current from it was just overclocking my readout meter, so it couldn't bleed off charge fast enough. You could see nice plume formation from the thruster and quite stable as you have plasma bridging between the hollow cathode and the anode, operating on both are operating on the adamantane gas. So taking all the lessons learned from the prior tests, from this test, from the preliminary tests, and working extensively on the new design, this is the first shot at the AIS-AHTI-PQ Pico anode layer Hall thruster. So the size of this thruster is about 0.1 U, and that actually includes everything. That includes the electronics, fuel, the valve, heater, the Hall thruster head itself. So at this point, as far as I'm aware, the smallest Hall thruster systems on the market are about 1 U in size. So this takes it down by an order of magnitude in volume, as well as over an order of magnitude in cost. It really opens up Hall thruster technology now to really any level. So the fuel, again, is adamantane. It has an 18-gram capacity, so 6 times the capacity of the original EHT1 prototype in a much smaller form factor, so much more efficiency in terms of space for fuel storage. The expected thrust is going to be anywhere from 10 to 50 micronewtons. This has to be directly measured and, again, widely varies based on the final power supply used, so the voltage, the discharge current, and the fuel flow rates. So there's kind of just a rough approximation of the estimate of what it's looking to achieve. Total system power is about 10 watts or less, so 2 watts for the actual discharge itself, and then the rest of the power is budgeted for the heater and the electronics. ISP is very difficult here at this point, but it is safe to say that it will be less than 500 seconds just to looking at scaling and extrapolating from other systems in the field of similar scales. As far as I'm aware, this is actually the smallest full Hall thruster system ever designed and built in the field. And there have been much smaller Hall thruster heads at a few millimeter discharge channel, where the the actual head here is about 20 millimeters in diameter. But the actual supporting infrastructure and all the scaling is still much larger for these other systems. So this really compactifies everything into a tight package that can be integrated on a PocketQube. So one of the key things about this thruster is also neutralizerless operation. And typically with ion thrusters, you need a neutralizer for charge neutralization, and for Hall thrusters, establishing the discharge. However, there's specifically for anode layer ion sources in industry, it's well known that self-sustaining discharge vacuum mode can be utilized by connecting the casing to ground and having the discharge established between the anode and the pole pieces. So in this vacuum mode, you can run at much lower pressures, down to 10 to the minus 5 torr on minimal gas flows with really any gases. So that really increases gas utilization efficiency for the system. However, the cost now is going to be thrust of power, whereas typical anode layer and stationary layer have discharge current to beam current efficiencies of 80 to 90%. This is going to drop down to about 10%. So you have a massive hit in thrust. However, for the cost of form factor and simplification and overall size and cost, this opens up a lot of interesting applications. So here we can actually see some of the parts. So on the left, you actually have the tank. So again, you have a heater that sits right under the fuel tank that directly heats and sublimates the fuel. You have a slot for the micro, the micro valve that is used to gate the sublimated fuel. You have an adapter plate, and then you have the Hall thruster head on the right side that sits right above it. So this is the Hall thruster without any of the internals. You can see various mounting points, threaded ports, and then ports for various magnet configurations. So another look on the inside. So again, this extreme miniaturization is through extremely tight integration. One of the keys to this was the use of solid sublimating fuel, which allows me to eliminate pressurized fuel tanks, all fuel feed lines, and just have direct integration from the fuel side to the thruster side. So the thruster head mounts directly to the top of the tank. The fuel valve mounts directly into the tank, and fuel is sublimated directly in and feeds right into the Hall thruster head. And for the electronics, I was able to actually get the electronics to fit around the entire thruster head on the top to allow it to keep within a PocketQube compatible form factor. So this again is everything from electronics to fuel delivery and then readouts. And the thruster itself is meant to be very, very simple to operate. Just turn the valve on, turn the sublimation power on, and then turn the discharge voltage on. So very straightforward and simple operation. So again, key factors for this type of scaling, because as far as I'm aware, when I first started this effort, I didn't think scaling a Hall thruster would be even remotely possible to PocketQube sizes, and I've been working on this for quite a while. But it turns out there's a few key aspects that have allowed this. First is the adamantane fuel with the unpressurized fuel feed and low power for sublimation and ionization. Use of a micro solenoid valve, which has been actually developed specifically for CubeSat propulsion applications. The design leverages industrial ALIS designs as opposed to standard Hall thruster topologies, just because what's out there currently doesn't fit at this scale. So I had to borrow from other resources, specifically industrial ion beam processing, which simplifies and makes the design much, much easier and simpler to fabricate. And then, of course, neutralizer or ALIS operation makes it much lower power and just easier in general to operate, and keeps the form factor much smaller. So here's kind of a look at the first iteration of the Hall thruster head. So I actually took inspiration from the EHT1. So there's a few stacks of off-the-shelf ceramic insulators that sandwich a anode, which discharges between the central pole piece and the outer pole piece. This was unsuccessful. As you can see here in this video, you can see a little bit of spurts of plasma as the thing tries to start up. But really, the topology, and there's a lot of issues with this particular design that led to the inability to actually fully ignite. So on the next iteration, I completely rebuilt the internals. So I substituted everything for a single 3D printed piece using Somos Perform, which houses a new smaller ring anode to address both fuel flow issues as well as some issues with the prior anode being too deep and arcing internally inside of the thruster instead of the upper pole pieces. So you can see a cross section of the thruster on the left and kind of the anode with the insulator on the right without the upper pole cap on. You can see the magnetic assembly going around. So again, this test gave a little bit more stable output. You can see a tiny slight glow, and sputtering a little bit, but still did not achieve full ignition. So moving on, I attempted a unusual segmented anode with some copper finger stock to try to increase the ionization of the fuel and make breakdown easier inside the thruster head. This also was not successful. This is not plume. This is not ignition. This is arcing and discharge with the adamantane gas flowing, but you can see that there's no proper anode layer formation being established, and the discharge is being kept concentrated along the sharp points, which is obviously not good for ignition. Next, I decided to go back to the stainless steel ring anode and switch in a higher power supply. So instead of a 2-watt discharge supply, I tried a 9-watt discharge supply just to see if the discharge current would have any effect on ignition. So this is the most recent test. This occurred about 3 weeks ago. So a lot more of activity. This again is not ignition. You can see tons of sparks sputtering, tons of plasma as the thing tries to sputter up and fire. So the internal pole pieces are actually kind of being eaten by the plasma a little bit here, and you can see lots of sparking and particulate emissions from the actual electrodes inside. Some plume, but still not full ignition. And going back, there are a number of reasons why this particular system could not be ignited in its current state. So moving forward, this is the new design that's in production. So I went back, I recalculated parameters for the anode layer topology. So first off, in the prior test, the magnetic field strength was way too high. It was actually causing the initial ionization arc to extinguish very rapidly, which is why you could see a lot of pulsing in some of the videos. The fuel flow path has been greatly improved. The anode shape has been greatly improved, and with better anode isolation. The anode design itself is much better. This is more consistent with traditional anode layer sources. And one of the biggest issues from prior tests was that the super thin ring anode is just too thin to establish a proper anode layer condition for the plasma formation. And then going back, I recalculated and I redesigned the channel widths and the depths to be more consistent. So I believe this current design should actually be successful at igniting with these new changes implemented. And again, a new cell must perform insert to hold the anode and direct fuel flow up all in one structure. So currently the system has achieved, I've validated sublimation system, so very even and uniform sublimation of the fuel. The HV discharge and readout circuit has been validated. Valve controller has been validated, and the full system has shown a very high uniform heating and no recondensation of the solid fuel within the system, which is very good, particularly for solid sublimating fuels. So the next steps will be to test the new V3 system, which will probably occur in about 3 weeks once the new internal parts, the anode and the pole pieces, will be manufactured. Then after that will be full system testing with valve cycling and fuel control. And finally, lifetime and characterization tests with the full thruster operating. So you can follow this work along a number of channels. I do everything very openly. So everything you see here has pretty much been shared on Twitter. And I do it pretty real time. I do everything literally at home in my basement. I'm not a startup that is spun out of a university or some incubator. This is all just kind of on my free time. With the vacuum system, developing and testing and building it right here at home. So you can see everything as it goes real time, and I really strive for as much transparency as possible. So you see everything from catastrophic failures to successes. So hopefully in the next few weeks, we'll actually be seeing full ignition of this new Hall thruster, and then moving forward, some more exciting tests to come with that.